Tonight, we will begin with an answer that sounds completely certain. It arrives in a calm, polished sentence. The grammar is clean. The name is specific. The date is precise. Nothing in the rhythm suggests hesitation. And the answer is wrong. We are going to follow that sentence backward through the machinery that produced it. We will pass through token probabilities, confidence scores, repeated samples, clusters of meaning, retrieved documents, external tools, and the quiet decision not to answer at all. The question is not whether artificial intelligence makes mistakes. Every useful system makes mistakes. The deeper question is whether a system can recognize the shape of its own uncertainty before a fluent guess becomes someone else's fact. There is no single meter inside a language model labeled truth. A probability over the next token is not the same thing as a probability that a complete claim is correct. Yet research suggests that models sometimes contain useful signals about what they can and cannot answer. Those signals can be measured, trained, compared, and connected to evidence. They can also fail. You do not need to remember the equations or the names of every benchmark. Let them move past like instruments in the midnight observatory. For now, imagine context holding one luminous sentence beneath a science scanner. It looks stable. One amber light says that something does not fit. Chapter 1. The answer that sounded certain. A person asks a question about an obscure event. The question contains enough familiar pieces to suggest an answer. There is a place, a historical period, a type of institution, and a person whose name sounds plausible beside the others. The model begins to generate. At each step, it considers possible next tokens. Some continuations receive more probability than others. A common phrase may be highly likely. A rare name may be less likely. The decoding process selects tokens until a complete response appears. The result can be remarkably coherent because coherence is deeply represented in the patterns the model learned. Names resemble names. Dates fit grammatical slots. Explanations follow familiar shapes. A paragraph can satisfy the form of an answer without maintaining a reliable connection to the event being described. People often call this a hallucination. The metaphor is imperfect because a language model does not experience an image or believe a private story in the human sense. A more precise word for one important failure mode is confabulation, an answer whose content is not reliably anchored, even though its form is fluent. Fluency makes the error difficult to notice. Human conversation contains signals of uncertainty. We pause. We search for a word. We say that we are unsure. These signals are not perfect. A confident person can be wrong, and a careful person can sound hesitant while being right. Still, ordinary speech gives the listener clues about the speaker's relationship to the claim. A generated sentence may not offer those clues unless the system has been designed to produce them. The same decoding machinery can state a well-known fact and invent an obscure citation with nearly identical style. Truthful QA was created to test a related problem. Its questions were chosen because people often answer them with common misconceptions. A model trained to imitate human text can reproduce those misconceptions. The false answer is not random. It is supported by patterns in the training distribution. This distinction matters. Some wrong answers arise because the model has little stable knowledge and different samples wander among possibilities. Others arise because the model consistently learned a false association. The first kind may look uncertain when sampled repeatedly. The second can remain confidently wrong. Our polished sentence is placed on the observatory table. Before asking whether the model knows it is wrong, we must ask what the word knows could mean for a machine that generates one token at a time. Chapter 2. Probability is not truth. Suppose the sentence begins with the words, "The bridge was completed in." The model may assign probabilities to several possible years. These probabilities describe how well each continuation fits the context according to the model. They are shaped by training data, model parameters, the prompt, and the tokens already generated. If 1 year has the highest probability, that does not automatically mean the model has estimated the historical chance that the bridge was completed in that year. The number belongs to a prediction problem over text. Sometimes textual probability and truth align. A well-known fact appears in many reliable contexts, and the correct continuation dominates. Sometimes they separate. A popular falsehood may be easy to predict. A true but rare fact may be difficult. A grammatically natural invented name may receive more probability than an awkward correct one. This is the first instrument we must calibrate carefully. For a simple classifier, uncertainty can look direct. A model assigns 70% probability to one class and 30% to another. Across many cases where it says 70%, roughly 70% should be correct if the system is well calibrated. Language generation is more complicated. An answer consists of many tokens. The same meaning can be written in many ways. Long answers accumulate many token probabilities. A rare spelling can make a correct sentence look improbable, while a common phrase can make an incorrect sentence look smooth. Researchers have therefore explored other questions. After a model proposes an answer, can it estimate the probability that the answer is true? Before answering, can it estimate the probability that it knows enough? Can information from hidden representations predict when the final result will be correct? Experiments have found encouraging signals. In language, models mostly know what they know. Larger models performed useful self-evaluation in several tested formats. They could estimate P true for proposed answers and PIK, the probability of I know, for questions. Relevant source material and helpful hints changed these estimates in sensible directions. But the phrase mostly is important. Calibration varied. Generalization to new tasks was imperfect. A model trained or prompted to express uncertainty in one setting may not carry that behavior reliably into another. The machine may contain information related to its likelihood of success, without possessing one universal, trustworthy confidence number. Uncertainty itself has more than one source. In statistics and machine learning, researchers sometimes distinguish aleatoric uncertainty from epistemic uncertainty. Aleatoric uncertainty belongs to variation or ambiguity in the situation. If a fair coin has not yet been tossed, no amount of study reveals the future result with certainty. If a question genuinely supports two interpretations, the ambiguity is part of the input. Epistemic uncertainty comes from limited knowledge or an imperfect model. More relevant evidence, a better representation, or additional training may reduce it. The boundary between these categories is not always clean for language. A question may be ambiguous because context is missing. A factual answer may be unknown to the model but available in a document. A future event may contain both predictable structure and irreducible variation. Still, the distinction helps choose an action. Missing knowledge suggests search. Ambiguity suggests clarification. Randomness suggests a distribution rather than a single prediction. A model that reports only one generic confidence score hides these different roads. There is also uncertainty about the model itself. A system may work well on familiar questions and poorly on a new dialect or domain. The uncertainty estimator was trained on yesterday's errors, while tomorrow's failures take a different shape. This is why uncertainty should be treated as an object that needs evaluation, not a decorative number added after the answer. Context separates three dials on the table. One is labeled likely continuation. One is labeled estimated correctness. One is labeled sufficient evidence. The dials sometimes move together. They are not the same instrument. Chapter 3. A weather forecast for answers. Calibration is easiest to understand through weather. Imagine collecting many days on which a forecast predicted a 30% chance of rain. If rain occurred on about 30% of those days, the forecasts were well calibrated at that level. This does not mean any single afternoon was 30% wet. It means the confidence number described a reliable pattern across comparable predictions. An AI answer can be evaluated in a similar way. Gather many questions for which the system reports 80% confidence. If only half the answers are correct, the system is overconfident. If nearly all are correct, it is underconfident. Calibration is not the same as accuracy. A cautious system could be well calibrated and often uncertain. A highly accurate system could still be dangerously overconfident on the few cases it misses. For decision-making, both properties matter. There is also a problem of grouping. Confidence may be reliable for arithmetic and poor for obscure biography. It may work on questions similar to the evaluation set and fail after a change in language, topic, or user behavior. A single average can hide these regions. This is known broadly as distribution shift. The world presented during deployment does not perfectly match the world used for training or calibration. Reliable uncertainty is most valuable in unfamiliar situations, precisely where calibration is hardest to establish. Prompting a model to say how confident it feels may provide some signal, but words such as probably and certainly are also generated language. They can reflect style, instruction following, or learned conversational habits. Research has found that prompting alone is not consistently enough for good calibration. Training on graded correct and incorrect examples can improve uncertainty estimates in studied settings. A useful system therefore needs records. It must compare previous confidence with actual outcomes. It must discover where its estimates drift. It may need separate calibration for different tasks and levels of consequence. Consider two answers with the same estimated chance of error. One selects a color for a decorative icon. The other summarizes evidence for a safety decision. The uncertainty number may be identical while the correct action is different. Confidence is not a command. It is one input to a policy. The observatory display now shows a curve rather than a single light. Along the curve are many past answers, each paired with what happened afterward. The system's honesty is measured not by how humble it sounds, but by whether its confidence survives comparison with reality. Chapter 4. Asking the same question again. One way to inspect uncertainty is to ask the model more than once. Generation includes choices. With sampling enabled, the same prompt can produce different continuations. For an easy, well-supported question, many samples may converge on the same answer. For an ambiguous or poorly represented question, they may spread across several possibilities. This gives us a simple intuition. Agreement suggests stability. Disagreement suggests uncertainty. Self-consistency methods use a related idea for reasoning tasks. Instead of relying on one reasoning path, the system samples several paths and selects the answer that appears most consistently. In published experiments, this improved results on a range of arithmetic and common sense benchmarks. The method works because a problem may have several valid routes to one solution. Errors can vary across routes, while the correct destination appears repeatedly. But repetition is not proof. If every sample begins from the same false association, all of them may agree. If a prompt strongly suggests an incorrect premise, the answers may consistently follow it. If training data contains a popular misconception, sampling can reproduce the same misconception many times. There is also a cost. Generating 10 answers uses more computation than generating one. A deployed system must decide when additional samples are worth the delay and energy. The pattern of disagreement still contains useful information. Imagine 10 cards placed on the table. 4 name one person, 3 name another. The remaining 3 offer different possibilities. The spread tells us that the first polished answer was not stable. Now imagine 10 cards that use different sentences, but all mean the same thing. Counting exact wording would exaggerate disagreement. We need to group answers by meaning. This brings us to entropy, a measure related to how spread out a distribution is. When nearly all probability lies on one outcome, entropy is low. When probability is distributed across many outcomes, entropy is higher. For language, the relevant outcomes are not always strings. Paris, it is Paris, and France's capital is Paris use different tokens but express the same answer. Context gathers the cards into small circles. The words differ. The meanings begin to form clusters. The quality of the samples matters. If every answer is generated with nearly deterministic decoding, repeated calls may produce identical text even when the underlying model would assign meaningful probability to alternatives. If sampling is too random, irrelevant variation can make a stable answer look uncertain. The temperature and decoding rules change what the experiment reveals. Independence matters as well. 10 samples from one model are not the same as 10 independently trained models using different data and methods. An ensemble can expose disagreements that one model's sampling distribution does not contain. But ensembles cost more, and several models may still inherit the same popular error. The question is therefore not simply how many answers agree. It is what process produced the answers, what kinds of diversity the process can express, and whether agreement has ever been compared with outcomes. Sampling becomes an instrument. Like any instrument, it must be configured and calibrated before its reading can be trusted. Chapter 5. Meanings not merely words. Semantic entropy is an attempt to measure uncertainty over meanings rather than surface forms. The procedure begins by sampling several answers. It then groups answers that are semantically equivalent. If two sentences entail each other, they can be treated as members of the same meaning cluster. The distribution across those clusters is used to estimate uncertainty. Low semantic entropy means that samples concentrate on one meaning, even if they phrase it differently. High semantic entropy means that the model produces several incompatible meanings. Research published in Nature in 2024 evaluated this method across question answering, mathematical word problems, and generated biographies. Semantic entropy outperformed several baseline uncertainty measures for detecting an important class of confabulations in the tested settings. The insight is elegant because it respects a basic property of language. Variation in wording is not necessarily variation in belief or answer. A naive measure can mistake paraphrase for doubt. Semantic clustering tries to remove that confusion. The method can also work when exact internal token probabilities are unavailable. A discrete approximation counts how many sampled answers fall into each semantic cluster. This makes the idea usable with black box systems, though sampling and semantic comparison still require computation. Consider our obscure historical question. 10 answers produce 3 different dates. 5 samples support one date, 3 another, and 2 a third. The meanings are genuinely different. Semantic entropy rises, warning that the answer may be a confabulation. Now consider a well-known capital. 10 answers use 6 phrasings but 1 meaning. Semantic entropy remains low. This is a detector, not an oracle. It is designed to notice arbitrary uncertainty in meaning. It does not prove that the dominant cluster is correct. 10 answers can agree on the same falsehood. A model can be uncertain for harmless reasons, such as a genuinely ambiguous question. Semantic grouping itself can make mistakes. The Nature study explicitly distinguishes confabulations from consistent errors. The method addresses a substantial failure mode, not every possible failure. Still, a detector changes what a system can do. High semantic uncertainty can trigger retrieval, request clarification, call a tool, generate additional checks, or abstain. Instead of showing the user an invisible warning number, the system can change its behavior. The amber light on the observatory table is no longer decorative. It opens a door. Long answers require another refinement. A paragraph can contain one well-supported fact, one reasonable inference, and one invented detail. Assigning one confidence score to the whole paragraph compresses these differences. The safest sentence can hide the weakest claim. Claim-level analysis breaks an answer into smaller factual units. Each unit can be checked against samples, sources, or tools. A biography might contain a correct birthplace, an uncertain date, and a fabricated award. The overall prose is neither simply true nor simply false. The semantic entropy research explored a related procedure for longer passages by decomposing text into factoids and generating questions connected to each factoid. Uncertainty could then be estimated around the individual claim rather than the entire paragraph. This creates a more useful display for people. Instead of one confidence badge, the answer can distinguish direct evidence, supported synthesis, uncertain inference, and unresolved detail. Such a display must remain understandable. Too many warnings can become visual noise. Users may ignore a page covered in caution symbols. The system needs to surface uncertainty where it changes a decision, while preserving access to the underlying evidence for those who need to inspect it. Chapter 6: The Confident Shared Mistake. Behind the door is a harder problem. Every sampled answer agrees. The confidence estimator is high. The prose is clear. The answer is still wrong. This can happen when a false pattern is stable inside the model. Perhaps the training data repeated a misconception. Perhaps the question contains a false premise. Perhaps the model learned a shortcut that works on typical examples and fails on this one. Uncertainty methods based on variation may not detect a shared mistake because there is little variation to measure. Human groups face a similar difficulty. Agreement among witnesses is powerful when their observations are independent. Agreement is weaker when everyone copied the same source. 10 websites can repeat one error while appearing to provide 10 pieces of evidence. Model samples are not fully independent witnesses. They come from the same learned system and often the same prompt. Their agreement is evidence of internal stability, not independent confirmation from the world. This is where calibration based on past outcomes can help, but it also has limits. If the new question belongs to a hidden region where the model's errors are systematic, average calibration may look reassuring. Adversarial benchmarks such as Truthful QA try to expose these regions by asking questions that invite familiar false answers. The benchmark demonstrates why general fluency and ordinary task performance do not guarantee truthfulness. The solution cannot be one more phrase instructing the model to be careful. A system may need evidence that did not originate from the same internal pattern. For arithmetic, the evidence can be a calculator. For code, it can be a compiler or test suite. For a factual claim, it can be a reliable document. For a scientific question, it may be a database, a measurement, or a formal model. For a user's intent, it may be a clarifying question. The important motion is outward. Instead of asking the generator to judge only itself, the system creates contact with a source that can disagree. Context moves the 10 identical cards aside. Behind them is one small window. The window does not speak fluently. It shows a dated record. Even external evidence can share an origin with the mistake. A search result may quote an article that quoted another article that copied a generated summary. Several sources can appear independent while tracing back to one unverified claim. Source counting without provenance recreates the same problem as sample counting. Reliable verification therefore asks not only whether sources agree, but how they know. A primary measurement differs from a commentary. An official record differs from an unattributed list. A later correction may be more important than an earlier widely copied error. Time matters. A claim that was correct last year may be wrong today. A confidence estimate based on training can remain internally stable while the world changes. Retrieval should carry dates, and the final answer should distinguish historical knowledge from current state. There are also questions for which no external source can decide the matter. Values, preferences, and forecasts involve judgment. The honest system should not disguise a choice as a fact merely because it can retrieve supporting quotations. Evidence is a relationship between a claim and a source, not a pile of links. Chapter 7. Opening the Evidence Door. Retrieval augmented generation gives a model access to documents selected for the current question. The system converts a query into a search, retrieves candidate passages, places relevant material into context, and generates an answer conditioned on that material. This can provide information that was absent from the model's parameters, more recent than its training, or specific to a trusted collection. Retrieval creates a path to evidence. It does not guarantee correctness. The search may retrieve the wrong document. A relevant passage may be ranked too low. The source itself may be unreliable. The model may misread a correct passage or combine two passages incorrectly. A citation can be present while failing to support the nearby sentence. A mature system must therefore evaluate the whole chain: query, source, passage, interpretation, and final claim. Tools extend the chain beyond documents. React and related approaches interleave language model reasoning with actions in an external environment. A model can issue a search, call a calculator, inspect a database, run code, or observe the result of an operation. The observation returns to the model as new context. This changes uncertainty from a description into a routing decision. If arithmetic confidence is low, call the calculator. If a fact is recent, search a dated source. If a request is ambiguous, ask the user. If a claim is consequential and evidence remains weak, route it to a person. The system also needs to know when tools fail. A database can be incomplete. A search can return nothing. A calculator can receive the wrong expression. Tool use does not remove uncertainty. It rearranges it into components that can be inspected. Evidence should remain visible enough to audit. A trustworthy answer can state which claims came from which sources, what was inferred, and what remains unknown. This is more useful than attaching a vague confidence percentage to a long paragraph. Different claims inside the paragraph may have different support. On the observatory wall, one answer becomes a map. Some lines lead to documents. Some lead to calculations. One line ends in darkness. That unfinished line is not hidden. It becomes the reason to stop. Chapter 8. The Art of Not Answering. Abstention is the ability to withhold an answer when evidence or confidence is not sufficient. It sounds simple. A model can be prompted to say, "I do not know," but a reliable abstention policy must balance two errors. Answer too often and the system presents guesses as facts. Refuse too often and the system becomes safe but useless. Researchers describe this balance with ideas such as coverage and selective risk. Coverage is the fraction of cases the system chooses to answer. Selective risk is the error rate among those answers. As the confidence threshold rises, coverage usually falls while reliability among answered cases may improve. There is no universal correct threshold. A bedtime recommendation for a fictional character can tolerate more uncertainty than a decision about real infrastructure. A brainstorming tool can offer uncertain possibilities if they are labeled as ideas. A factual reference system should demand stronger evidence. The cost of a false answer, the cost of delay, and the availability of human review all matter. Good abstention is also informative. Instead of a flat refusal, the system can say what is missing. The date cannot be verified. The question has two interpretations. The available sources disagree. The requested prediction exceeds the evidence. This turns uncertainty into a next step. The system can request a document, narrow the question, propose a safe experiment, or explain which assumption would change the answer. It remains useful without pretending to know. Training this behavior requires examples of correct answers, incorrect answers, and appropriate refusals. Evaluation must test unfamiliar domains and adversarial prompts, not only cases where uncertainty is easy to detect. There is a cultural challenge as well. Users often reward immediate certainty. Products compete on speed and smoothness. A short, confident answer can feel better than a careful map of evidence. Trustworthy design may need to make honest uncertainty feel like competence, rather than failure. People interpret uncertainty through psychology as well as mathematics. A number such as 62% can appear more precise than the evidence justifies. A verbal phrase such as likely can mean different things to different readers. A warning placed after a long, confident paragraph may have little effect. The interface can connect uncertainty to action. This answer is based on one source. These records disagree. This calculation was verified. This forecast depends on 3 assumptions. These are more concrete than a theatrical apology. Users also need a way to correct the system. If a person provides reliable evidence that an answer is wrong, the correction should influence the current task and, where appropriate and permitted, future behavior. The system should preserve provenance for the correction, rather than merely replacing one unsupported claim with another. Institutions may set different thresholds. A creative studio, a school, and an engineering team have different consequences and review processes. Reliability is partly a property of the surrounding workflow, not only the base model. An AI that abstains at the right moment can still be used badly if people remove the warning or automate the final decision without review. Conversely, a limited model can be useful inside a carefully designed process with strong checks. The question, "Can AI know when it is wrong?" eventually becomes a question about a whole system. Model, tools, interface, records, incentives, and people. Context dims the answer panel but leaves the path forward illuminated. The machine has not become silent. It has changed the form of help. Chapter 9. An honest machine at the observatory. We can now return to the first polished sentence. At the beginning, it looked complete. Now it appears as one object in a larger system. The token generator produced it. A self-evaluator estimated whether it was likely to be correct. Repeated samples revealed whether alternatives existed. Semantic entropy grouped those alternatives by meaning. Calibration records compared past confidence with outcomes. Retrieval opened a path to documents. Tools tested what could be tested. An abstention policy considered the consequence of being wrong. No layer supplied perfect certainty. Together, the layers changed the decision. This may be the most useful interpretation of an AI knowing when it is wrong. not a machine possessing a human feeling of doubt, and not one magical confidence number, but a system capable of detecting several kinds of weakness and responding appropriately. Some uncertainty comes from many plausible answers. Some comes from missing information. Some comes from an ambiguous question. Some errors remain invisible because the model learned them consistently. Each condition requires a different response. A mature assistant might separate claim from evidence, estimate uncertainty at the claim level, select tools based on the failure mode, and preserve a record of what was checked. It might know that a low-stakes creative task invites exploration, while a consequential factual task demands restraint. This is partly an engineering problem and partly a design choice. A system optimized only to produce an answer may learn to perform certainty. A system evaluated on calibration, evidence, correction, and appropriate abstention can learn a different habit. There will still be mistakes. Confidence estimates will drift. Sources will conflict. Tools will fail. People will disagree about acceptable risk. After an answer is delivered, the work can continue. A deployed system can monitor which answers are corrected, which tool calls fail, where users request clarification, and which confidence ranges prove unreliable. These observations create a feedback loop grounded in outcomes rather than in the model's own prose. Monitoring must be designed with privacy and consent. A useful correction should not require collecting every private conversation. Aggregate evaluation, carefully selected review sets, local processing, and explicit user reports can provide signals without turning uncertainty measurement into unlimited surveillance. Corrections also need versioning. If a source changes, the system should know which answer relied on the earlier version. If a calibration model is updated, engineers should be able to compare its decisions with the previous one. Trust grows when a failure can be reconstructed. This suggests a quiet maintenance cycle. Predict, estimate uncertainty, root the case, observe the result, review the failure, recalibrate. The cycle does not make the machine infallible. It prevents yesterday's confidence from becoming a permanent excuse. Benchmarks remain useful inside this cycle, but live errors reveal boundaries that benchmarks did not anticipate. A rare user question can expose a new region of uncertainty. A changed database can reveal dependence on stale evidence. A tool outage can show that the fallback policy answers when it should wait. The ability to know when one is wrong is therefore partly the ability to learn from being shown that one was wrong. Honesty does not mean the absence of error. It means that uncertainty is not hidden behind fluency and that correction remains possible. In the Midnight Observatory, context places the original sentence beside the dated record. The name was wrong. The structure was elegant. The correction is smaller than the answer, but it carries a line back to evidence. The science scanner closes. One amber light remains, not as an alarm, but as a reminder that every answer has a boundary. The most trustworthy machine may not be the one that always speaks first. It may be the one that knows when to search, when to test, when to ask, and when to leave a space where an unsupported answer would have been. For tonight, that space can remain quiet. There is nothing more you need to decide. Good night.